So until now we have studied the relation between current I and current density J bar, that is derived as I equal to closed surface integral of J bar dot ds bar. This is one relation that we have derived, and next derivation that we have seen is relation between current density J bar and volume charge density rho v, that is given as J bar equal to rho v into V bar. Okay, J bar is the current density in vector form, rho v is the volume charge density, and this V bar is the velocity in that particular direction which you are considering. So these are the two relations that we have derived. Keep them aside. Now we are going for a new topic called as continuity equation. Continuity equation, which is very important. Continuity equation, this topic is repeated many times in your previous year papers. So this continuity equation also gives the relation between charge Q, current and the current density J bar. So already we have defined what is meant by electric current, what is meant by conventional current, displacement current, drift current and all those. So basically if you go for electric current is flow of electrons. Electric current is flow of electrons or negatively charged particles. If you consider the conventional direction of current, if you take the conventional current, then that is given as conventional current is the flow of protons, positively charged particles. Electrons are negatively charged particles, protons are positively charged particles. So conventional current is always opposite to the electric current. That means flow of positively charged particles is your actual current I. Now if you consider a small circuit like this, so how will be your conventional current? Conventional current will be from high potential to low potential. That means the flow of protons, the flow of positively charged particles is the conventional current, and your electron direction is opposite. Your electron direction is opposite. That means like this you can take the electric current direction. So conventional current is from high potential to low potential, electron current is opposite. If you consider only the conventional current, now leave about the flow of electrons. For our convenience, we are fixing that conventional current is the main current, that means flow of protons, positively charged particles. So I am considering only the conventional current I. So consider this charged body, this source is a charged body, it is giving away the charged particles to some load. Okay, that means if you consider the conventional current direction, the positive charges are passing out of that closed surface. Positive charged particles are passing out of the body. Conventional current if you take means positively charged particles are flowing out from the closed surface, closed charged surface that you are considering. Positively charged particles are flowing outwards, from the closed charged body. If a body is continuously giving away the charge, that means if there is charge in me, if I am continuously giving away the charge, finally what will happen to the charge that is present in me? That will decrease slowly. That means dq by dt can be given with negative sign or positive sign. Current is actually given as dq by dt. But here, as the charged particles, positively charged particles are going outwards. If you consider this as a positively charged body, closed surface, then it is giving away the positively charged particles. Then what will happen to the rate dq by dt for this source or charged body? That rate will decrease. Minus you should keep, because as it is going on giving those charges, the amount of charge that is present in this charged body will slowly decrease. That's why we are keeping minus sign. This minus dq by dt why we are keeping means rate of decrease in the charge. Rate of decrease in the charge in the charged body. So this we can express only if we consider conventional current only. Conventional current means flow of positively charged particles. If we consider the conventional current, you can observe that this charged body is giving away the positively charged particles out of it. That means charge is passing outwards from the closed body. As it is giving away the charge, what will happen to the rate of the charge inside the charged body? That rate of the charge inside the charged body will decrease because it is going on giving the charges that is present in it. So rate of decrease in charge we can write inside the charged body. Okay, so that's why I am expressing minus dq by dt. But what is the general relation between I and j bar? Already we have derived that I equal to closed surface integral of j bar dot ds bar. Now this I in this charged body, when you consider this conventional current, is also I equal to minus dq by dt. So can we equate I equal to minus dq by dt is equal to, what is I value? That is closed surface integral of j bar dot ds bar. Okay, so this equation I equal to minus dq by dt integral of, that is equal to closed surface integral of j bar dot ds bar. This equation is called as continuity equation. This equation is the continuity equation in integral form. Continuity equation in integral form. Okay, so here first, during the derivation of continuity equation, we need to know what is meant by conventional current. The actual current is the flow of negatively charged particles, that is electrons. But for our convenience, we are taking conventional current, that means the flow of positively charged particles. If you consider a volume of the charged body, if it is giving conventional current, that means positively charged particles are flowing outwards. Positively charged particles are flowing outwards from the closed charged body. That means if there is a source, we can consider it as a volume of charged body. It is giving some conventional current, means positive particles are coming outwards from this body. As it is giving, it is going on giving the charge outwards. What will happen to the dq by dt inside this body? It will decrease. That's why I am writing minus dq by dt. So as it is giving away the positive charge, the charge inside that body will decrease. So I equal to minus dq by dt. Now, what is the relation between I and j bar? Already we derived that I equal to closed surface integral of j bar dot ds bar. So in the place of I can also write integral j bar dot ds bar. So finally, current I in a volume of charged body is equal to minus dq by dt. Why I am keeping minus means here the rate of the charge is decreasing as the volume of the body is giving away the charge. Charge is flowing outwards from the body. So inside the body charge is decreasing, that's why I am keeping minus sign. So I equal to minus dq by dt, that is equal to closed surface integral of j bar dot ds bar. This particular equation is called as continuity equation, that too in integral form. Next we should derive the continuity equation in point form. Okay. So one by one, what are the formulas we are deriving? Let us write on one side. First formula that we have derived is I equal to closed surface integral of j bar dot ds bar, and j bar is equal to rho v into v bar, where this v is the velocity of the charged particles with which they are moving. Next, continuity equation in integral form, that is I equal to minus dq by dt that is closed surface integral of j bar dot ds bar. These three equations we have derived. Now, this is the continuity equation in integral form. Suppose in our derivation we said that conventional direction is the direction of positively charged particles. That means charge is coming outwards from the body. That's why we have kept inside the body the rate of charge is decreasing, minus. Suppose if I take the charge is coming inside the body, then we can keep plus sign here. Okay. So let us assume that charge is going outwards only. Fix for this equation, continuity equation in integral form. Now to derive the point form of continuity equation, let us apply divergence theorem to the relation of I equal to integral j bar dot ds bar. Here we are having closed surface integral. Closed surface integral of j bar dot ds bar. By using divergence theorem, we already know that surface integral can be converted to volume integral. Surface integral can be converted to volume integral by using divergence theorem, which states that surface integral of j bar dot ds bar is equal to volume integral of del dot j bar, volume integral of del dot j bar into dv. This is the divergence theorem. Surface integral of j bar dot ds bar is equal to volume integral of del dot j bar dv. Okay, this is the divergence theorem applied to this formula. Now we can make some assumptions. Already we have derived some relations. In the place of j bar, what we can substitute? Rho v into v bar. Okay, like that. After substituting, we can obtain another form of continuity equation, that is point form. Now see, actually we know that I equal to minus dq by dt is equal to closed surface integral of j bar dot ds bar. This is the previous continuity equation in integral form. These are the summarized formulas. Now can we take closed surface integral of j bar dot ds bar is equal to minus dq by dt? Can we take this? Closed surface integral of j bar dot ds bar is equal to minus dq by dt. So in the place of this closed surface integral of j bar dot ds bar, can I write minus dq by dt, that is equal to volume integral of del dot j bar dv. Okay, volume integral of del dot j bar dv. We already know that rho v is equal to q by v. Volume charge density is equal to charge present in that volume divided by the volume of that body. Okay, so if you want the entire charge, first we are considering only differential charges. Then if we want the entire charge, then we can write q equal to volume integral of rho v dv. Okay, suppose if you take dq by dv, dq is equal to rho v dv. Suppose if I want complete charge q, then integrate on both sides, then you will get q equal to volume integral of rho v dv. So in the place of q, what I can substitute? Volume integral of rho v dv. So here what I will do means minus d by dt of, in the place of q what you can substitute? Volume integral of rho v dv. Volume integral of rho v dv, that is equal to volume integral of del dot j bar dv. Okay, so in the place of q what I have substituted? Q, in the place of q, volume integral of rho v dv I have substituted, minus d by dt of, in the place of q I have substituted volume integral of rho v dv. that is equal to volume integral of del dot j bar dv. Now, can we send this differentiation inside and this integration outside? So that will become volume integral of minus d rho v by dt. So as you are considering only a small differential parts, we can take it as dou, partial derivative dou rho v by dou t. See, I am sending this integration that side and I am moving this derivative inside. So volume integral of minus dou rho v by dou t dv is equal to volume integral of del dot j bar dv. So on comparing this LHS and RHS, volume integral is common on both sides, dv is common on both sides. Can we equate this remaining two terms? Del dot j bar is equal to minus dou rho v by dou t. So your final equation is del dot j bar is equal to minus dou rho v by dou t. Del dot j bar is equal to minus dou rho v by dou t. This is the continuity equation in point form or differential form. Okay, continuity equation in integral form is I equal to minus dq by dt, that is equal to closed surface integral of j bar dot ds bar. And now on further derivation we can obtain the continuity equation in point form, that is del dot j bar is equal to minus dou rho v by dou t. So let us summarize all these equations. So continuity equation means we should derive both integral form as well as point form.